Marhaban in lecture 8, segment 1, where we're going to discuss reactors and series, specifically CSTR and series. And segment 2, we're going to talk about plug flow reactors and series. Okay, reactors and series. Let's note the streams and reactor labeling. Okay, so here we have a bunch of reactors and series, and let's notice how we name them. Okay, we have 3 reactors, so the volume of the first reactor will be V1. Okay, so this basically will be R1, the volume will be V1. The second reactor will be R2, volume is V2. The third reactor is R3, and the volume is V3. Let's look at the stream labeling. Okay, so since this is R1, the stream following this R1 is stream 1. Okay, stream 1. Okay, and the one before it, it will be stream 0. So this is stream 1, this is stream 0. This is reactor 2, so the stream leaving reactor 2 is stream 2. Okay, stream 2, and the stream leaving reactor 3 will be stream 3. Okay, is that clear now? The labeling. Okay. Okay, very good. Express the conversion achieved by or inside reactor 3 symbolically. Okay, so I want to express x at R3 or x by R3. So what's the conversion achieved by reactor 3? Okay, the conversion achieved by reactor 3 is moles of A reacted divided by moles of A fed. So how do you quantify the mole of A reacted inside reactor 3? Well, basically we check how much input do we have. Fa2, okay, minus what is the molar flow rate leaving the reactor, right? So this is input, this is the output. Where did the difference go? Reacted, exactly, divided by the moles of A fed, which is Fa2. So this is how we define the conversion, or we calculate the conversion achieved by reactor 3 or inside reactor 3. Okay, many times reactors are connected in series so that the exit stream of one reactor is the feed stream for another reactor. For such cases, to speed calculation, conversion is defined in a new way. We have a new way of definition of conversion, that is xi. Xi is the conversion achieved up to point I with respect to the feed to the first reactor. So our reference is always the feed to the first reactor. Okay, so here if we say x2, that means this is the conversion achieved up to point 2. This is stream 2, this is point 2, so this is Fa2. Okay, this is x2, and we say x2, we are referring to the conversion achieved up to point 2 in reference to the feed to the first reactor. So this conversion x2 was achieved by whom? The credit goes to whom? Well, obviously it goes to reactor 1 and reactor 2 because they both helped in achieving x2 by lowering the molar flow rate from Fa1 down to Fa2. Okay, so that's what we mean by x2 as opposed to x at reactor 2 or x achieved by reactor 2, which is referring to the conversion achieved by reactor 2 only. That's different. Okay, so therefore xi is defined as the total moles of A reacted up to point I divided by moles of A fed to the first reactor, or we can write it as FAI minus, FA naught, okay, minus FAI divided by FA naught. Okay, let's express the conversion achieved up to point or up to stream 3 symbolically, x3. Shabab, how do you write it? Okay, so we write it as follows. x3 equals, it's always in comparison to FA naught, right? FA naught minus FA3 divided by FA naught. So this is x3 at point 3. Okay, so x3 is the total conversion achieved by all the 3 reactors up to point 3 compared to point 0 here. Okay, what is the other name of x3? It's the overall conversion, correct? Remember this from 111? Is the overall conversion achieved by all the reactors by the help of reactor 1, 2, and 3. Okay, so reactor 3 is the last reactor. X3 is also known as the overall conversion. Okay, excellent, Shabab, excellent. So if we choose this definition, this new definition, then FAI can be written as FA naught times 1 minus XI. That is, the remaining molar flow rate. The remaining molar flow rate equals, we're not talking about the fraction conversion, the fractional conversion of the fraction of the converted material up to point I. We're talking about the fraction not converted up to point I multiplied by the feed to the first reactor. So that gives you the remaining unreacted material. Okay, this is only good for reactors and series. Okay, please note, Shabab, it's not only reactors and series, it's reactors and series with no side streams, Okay, this is very important. So this definition can only be used when the feed stream only enters the first reactor. So the feed stream only enters the first reactor in the series, and there are no side streams, either fed or withdrawn. So there is no side stream, there is no A leaving here, right? Or there is no extra A fed here. Okay, so this definition is correct for reactors and series with no side streams. To demonstrate these ideas, we will consider 3 different schemes of reactors in series. We're going to go with 2 CSTRs in series, 2 plug flow reactors in series, then a combination of plug flow reactors and CSTRs in series. Okay, let's start with CSTRs in series. Starting from the general mole balance equation, derive the design equation for each of the shown reactors in terms of conversion. Okay, so for reactor 1, obviously we learned that the design equation is V1 equals FA naught over minus RA1 divided by X1. Remember, Shabab, the rate is evaluated at the exit conversion. Okay, good. What about reactor 2? In order to derive the design equation for reactor 2, we do the mole balance around reactor 2. Okay, so let's do that. Let's write the mole balance around reactor 2 for the species A. Okay, what does the mole balance say? Well, it says input. What do you have for input here? Well, we have FA1, right? That's the input to reactor 2. Minus output. What's the output of reactor 2? Obviously, it's FA2, correct? And plus generation. That's the integration for RA, right, dV from obviously x1, this is x1, from x1 to x2, okay, equals 0, because the CSTR is operated under steady state, so the accumulation is 0. Okay, great. So let's see. Let's write FA1. What does FA1 equal? Well, we can always refer it to FA0, right? So that would be FA1 equals FA0 1 minus x1. So basically is whatever I fed, right, times whatever not converted up to point 1, which is 1 minus x1, minus, what about FA2? Well, FA2 is evaluated also based on FA0, because remember, all the conversions that we deal with is in reference to FA0. FA0 times whatever not converted up to point 2, whatever not converted up to point 2, that is 1 minus x2, plus, let's look at the rate of reaction inside reactor 2. Let's look at the generation term inside reactor 2, right? When we say plus generation, we mean generation in this system, which we're doing balance around. Okay, so the rate of reaction in reactor 2 is not function of volume, because it's a CSTR, so it goes outside, right? It goes outside, and I'm sorry, I think I did a mistake here. This is not from x1 to x2. This is the generation inside reactor 2. So that's from 0 to V2. That's from 0 to V2. Okay, that's on the whole, on the complete reactor 2. Okay, so that means we have here RA, because it's not function of the volume, so it goes outside, and it says RA2. That means the rate of reaction inside reactor 2, integration of dV from 0 to V2. That means from the whole reactor, okay? The whole reactor from volume 0 all the way to the whole complete volume equals to 0. Okay, so let's open up the bracket here. We have FA0 minus FA0 x1 minus FA0 plus FA0 times x2, right, plus RA2, this is the rate of reaction inside reactor 2, times the integration of dV is V, evaluated from 0 to V2, that is V2 equals to 0. Let's see what cancels out here. Okay, so let's cancel out the FA0 here with the FA0 there, and let's take FA0 as a common factor. So if we take FA0 as a common factor, we'll end up with x2 minus x1, and then we can take this term to the other side, so we'll have minus RA2 multiplied by V2. Okay, so let's rearrange it. So we keep V2 in one side. Okay, let's write it here. V2 equals, now we have FA0 divided by minus RA2 times x2 minus x1. So now this is our design equation for the second CSTR in series. Okay, so here we go. That's the design equation for the second reactor. Recall that minus RA1 is evaluated at x1, and minus RA2, representing the rate of reaction inside reactor 2, is evaluated at x2. Great. Okay, for x1 equals 0.4 and x2 equals 0.8. Shade the areas that represent V1 and V2. So let's do that together. Okay, so let's see. For the first reactor V1, we have the width is actually x1, which is 0.4. So here we go. This is the width. Okay, and the height is not evaluated at 0, but evaluated at x1, which is 0.4. So this is the height, right? So width times the height gives you the area of a rectangle. Okay, see, area of a rectangle. Let's look at the second reactor, V2. That is the width. So the width is actually not x2, it's x2 minus x1. So x2, which is 0.8, okay, minus x1, which is 0.4. So this is the remaining. This is the remaining. Okay, so it's not from 0 to 0.8. It's not x2. It's x2 minus x1. So this is the width. What about the height? Is this the height here? No, it's not, because the rate is evaluated at the exit of reactor 2, which is x2. So this is the height. This is the height. This is the width, and this is the height. Correct? So if this is the width, so this is the width of the rectangle as well. So the width times the height gives you the area of a rectangle. Okay, please don't do the mistake of taking this area. Don't do this. Okay, please don't do this. This is not the area. Okay, this is not the area. Okay, this is the area. Tamam? Okay, great. Great. طيب, let's take an example. Example 2.5. Example 2.5. Comparing volumes of CSTRs and series. For the two CSTRs in series, 40% conversion is achieved in the first reactor. What is the volume of each of the two reactors necessary to achieve 80% overall conversion of the entering species A? So X2 is obviously 0.8, which is the overall conversion, and the intermediate conversion is 0.4. So reactor 1 takes you from conversion of 0 to 0.4. Reactor 2 takes you from the conversion of 0.4 to 0.8. So both of them are doing 0.4 conversion compared to the feed. So let's find the volume. Okay, so volume 1. Volume 1. How do you calculate volume 1? Well, volume 1, the reactor, well, the volume of the first reactor is achieving 0.4 conversion, right? So this guy is 0.4. At about this function, or the height, it's evaluated at 0.4. So this is the value. Okay, so it is 2.05 multiplied by 0.4. So that gives you V1. What about V2? Okay, what about V2? Well, V2, first we have to find X2. What is X2? It's 0.8 minus X1, which is 0.4, and multiplied by the FA0 over minus RA, which is evaluated at X2, right, at the exit, correct? Because the exit condition represents the condition inside the reactor. So this is X2, so therefore this is the FA0 over minus RA2, so that is 8. So this is 8 multiplied by 0.4. 8 multiplied by 0.4. This will give you the second volume. Okay, so V1 is 0.82 cubic meter, while V2 is 3.2 cubic meter. But don't you find this a little bit strange? Because both of them are giving you 0.4 conversion, 40% conversion. The first one takes you from 0 to 40%. The second one takes you from 40% to 80% conversion, based on a reference to the feed to the first reactor. So both of them are doing the same job. Why the volume the required volume of the first reactor is way less than the volume of the second reactor. This is really worth looking at. Okay, let's see. Are you thinking with me? Well, as we just learned from the previous lecture, that it's all about the reaction rate. The name of the game here is the reaction rate, correct? So let's look at the reaction rate. Okay, let's look at the first reactor. What's the rate of the reaction inside the first reactor? Well, first reactor, we're achieving 0.4 conversion, so the rate is around 0.2. 0.2. Okay, the rate is around 0.2 mole per cubic meter per second, right? Let's look at the second reactor. In the second reactor, we have a conversion of 0.8, right? So 80% conversion, only 20% of the material is left. So what's the rate of the reaction? Is 0.05. So this is minus RA1, this is minus RA2. Do you see the difference? It's 4 times bigger. The rate of reaction inside the first reactor is 4 times more than the rate of reaction in the second reactor. Therefore, the volume required for the first reactor is much smaller than the volume required for the second reactor, although both of them are achieving the same objective, or doing the same duty, which is a 40% conversion. Okay, so since the reactor 1 is achieving only 40% conversion, that means the concentration is relatively high compared to the second reactor, which is achieving, which you have by that time, by that location, you have 80% conversion. That means the majority of the moles converted. That means the concentration is relatively small. Therefore, the rate of reaction in the first reactor is significantly higher, or relatively higher, compared to the rate of reaction in the second reactor. And as we said, the volume is inversely proportional to the rate of reaction. Since the rate of reaction is very large in the first reactor, the required volume will be very small compared to the second reactor. So we explained why V2 is larger than V1, although both of them are achieving 40% conversion compared to the feed to the first reactor. Okay, now let's see something else. V1 was 0.82, V2 was 3.2, so the total volume was around 4 cubic meter. Okay, by comparison, V necessary to achieve 80% conversion in one CSTR, the volume as calculated was 6.4. So now we have 2 CSTRs in series to achieve an overall conversion of 80%, and their total volume is only 4 cubic meter. But if we use one CSTR, the volume is much bigger. It's around 6.4 cubic meter, although both of them are doing the same job, which is 80% overall conversion, right? We can also actually find out the difference between the volumes by looking at the Levenspiel plot, the shaded area. See that the area for the first reactor is here, the area for the second reactor in series is this, but if we compare it to the area for a single CSTR, it's this. So you can see that there is a big difference in the areas representing the big difference in the volume. And you can see that the difference is coming not from reactor 2 but from reactor 1, correct? That's the difference. See, that's the difference between the total volumes, and it's coming from the reactor 1 side. So let's try to understand why this is happening. Well, we said that everything is related to the rate of reaction in this course because it's a rate-based design, right? So let's see. Let's look at the rate. The rate at the first reactor, where you have a conversion of 0.4, the rate is around 0.2 mole per cubic meter per second. Okay, and the rate at the second reactor in series, where the conversion is 0.8, the rate is 1/4, around 0.05 mole per cubic meter. And the same thing with the one single CSTR, where you have the conversion is 0.8, the rate is also 0.05 mole per cubic meter per second. So as we said, higher rate of reaction will require less volume, correct? Will require less volume. Well, that's true. However, I cannot really now compare. So as you can see here, this number is similar to this number. As I said, the difference is coming from the first reactor, okay, where the rate of reaction is very high because we have only 40% conversion. That means the concentration still is high in the first reactor. So higher rate of reaction require less volume, but this comparison is not really fair yet, because you will tell me, yeah, I know that this volume is less compared to this volume, right? Because in the first reactor I'm only achieving 40%, while the single CSTR, one single CSTR, I'm achieving 80% conversion. Okay, this is only 40% conversion, this is 80% conversion. So obviously this volume will be less. So in order to make a fair comparison, let's calculate volume per conversion. Okay, so volume per conversion. So the volume of the first reactor is 0.82 divided by conversion. How much conversion? It is 0.4. So that is around 0.4. That is around 2. Let's say, yeah, that's around 2 cubic meter per conversion. Okay, per conversion. Let's look at this reactor, V over X. So here we have the volume is 6.4 and you're achieving 0.8. So the answer is 8 cubic meter per conversion. Okay, so because the first reactor in the reactors in series is operating at high rate of reaction, you require less volume per conversion compared to the single CSTR, where the rate of reaction is very slow, and therefore you will require more volume per conversion, around 4 times more. Hence, the total volume for this setup became less than the total volume in this setup, because the first reactor in the reactors in series setup is operating under high rate of reaction, therefore it requires less volume per conversion. Okay, I hope it's clear for you guys. There is one optional exercise here which you can do at home, and this will leave you with a question. What should be my intermediate conversion in order to obtain, or in order to minimize the total volume of the reactor? So for example 2.5, we said this is the question now, the optional question. For example 2.5, determine the optimum value of the intermediate conversion x1 that minimizes the total volume of the reactors, keeping the overall conversion at 80%. Because, you know, if the total, if the x1 was 80%. That means you don't need the second reactor. Then the volume of the reactor will be 6.4 cubic meter, correct? That if x1 was 0.8, meaning there is no need for the second reactor. If x1 was 0, meaning there is no first reactor, only second reactor, then also the volume will be 6.4. So what should be the value of x1 in order to minimize the total volume? Well, you can do iterative calculation here. So every time you change x1 and you calculate v1 and calculate v2 and then calculate the total volume, then you can plot this figure here, okay, and you can find that if x1 was 0.56, somewhere here, 0.56, then the total volume will be the smallest required volume. Okay, so that will even give you smaller volume compared to the case where x1 was 0.4. Okay, I'll leave you here and we'll meet soon inshallah in segment 2. Bye for now.